All right, hi everybody. We've got 40 minutes. I've got too much content. I've drunk too much caffeine, so this is going to be like a punk rock concert. Are you ready for 40 blistering minutes of queuing theory? I said, are you ready for 40 blistering minutes of queuing theory? All right, so am I. So let's say that you're going to adopt a services-oriented architecture. Some of them might even be micro, but it all starts with one application or service, right? You pull out some functionality. You get it ready for production. You get it set up, ready to take some traffic. And sure enough, you start to gather some traffic to your service. And then you start building more services. And they start attracting more traffic themselves. And before you know it, you have hundreds of services and thousands of clients. And you have to make sense of this somehow. And this is usually where you bring in something called an API management gateway. Now, there are really two things an API management gateway tends to do. One of them is authentication and authorization, right? We want to make sure that the people calling the services are actually allowed to do that. That's not what I'm going to be talking about today, because the other thing that they do is they provide capacity management, right? And one of the things that we want to be careful about is we don't want to let one client use too much of the capacity of a service and starve everybody else out. That's sort of like this method of dividing pie, right? Which is like, here's a slice for you, and I'm going to take the rest of the pie. So we don't want to have this going on. Now, the way that many API management gateways and the way that we think about managing access to APIs, they often use rate limiting. Okay, so this is the idea that I'm going to say, hey, you're allowed to use, say, 25 requests per second. To my service. So what I'm hopefully going to convince you of today is that this is not the best way to do it. And in particular, there's a couple of places where this doesn't work out so right. So the first one is in cases where the origin service has been overloaded. Okay, so it turns out rate limits don't work very well there. And then the second thing is that sometimes rate limits can be too aggressive. So sometimes we end up rejecting requests that we could have served otherwise. Okay? So that's what we're going to be talking about today. And everybody ready for the queuing theory? Okay, it is not going to look like this, so don't worry. This is all of the queuing theory that we're going to do today, okay? Is this simple equation, n equals x times r. This is known as Little's law. People who work with me know that I'm a big fan of Little's law. In fact, some folks I worked with have coined Moore's second law, which says that if John Moore has an opportunity to apply Little's law, he will. But this is super useful. I've actually used Little's law to debug performance problems with pencil and paper and just sort of asking another engineer how a service worked. So this is cool stuff. Okay, so let's go through what this is. So n is the average number of concurrent requests. So if we took a snapshot of the service, this is the number of requests that are currently in flight being processed by this request processing system. X is the average transaction rate. Okay, so this is the rate at which requests are arriving at the system. And then R is the average response time, okay, which is how long it takes on average to process one request. It's important to note that Little's law applies to averages, okay, so this is about capacity, it's not about performance. We all know we want to look at things other than average latency when we're trying to manage performance. But anyway, to put this into a context that hopefully folks are familiar with, how many people have been on an amusement park ride that either that's like this or you've seen a ride that's like this? Right, okay, lots of folks, okay? So put this in Little's law terms, okay? N is the number of people on the ride, okay? So if I took a snapshot of the ride, how many people would actually be on the ride? X is the rate at which people are arriving, wanting to ride the ride. And then R is how long the ride lasts, okay? Pretty straightforward. So now, of course, well, some of us may operate amusement park rides. I'm not sure, but when we're looking at computer systems, right? The question is, okay, so what is the equivalent of this? Okay, so what are the equivalent of the flying elephants here? So there are lots of places in our applications where you can think of a request being resident while it's being processed. Okay. And these are the things that really represent capacity in the system, right? These are the flying elephants. These are where the requests are sitting while they're on your ride, if you want to think about it. Okay, everybody with me so far? All right, so now we're gonna actually look at a couple of demos and get at some of these things. So just to get us squared away, we're gonna come over here. I've written a couple of applications. So we're gonna start with an origin service. and we're going to spin this up over here on a particular port. And now the way this origin service is going to work is it's going to have a fixed size thread pool. Okay, so I'm going to give it 7 worker threads. And then basically when a request arrives, we're going to hand it to one of the worker threads. The worker thread is actually just going to sleep because it's a demo and it doesn't actually have to do anything, so that's nice. But we're going to have it sleep on average for 1 second. Okay, and so this is a little Spring Boot application. We're going to spin this guy up. All right, now let's generate some load. So let's come over here, and I have another application, and so we're going to spin that up on another port. So I have this. This is really just listening on a port, so I can scrape metrics from it, so I can show you what's going on in a nice dashboard here. So we're going to give this a client ID. And we're also going to give this a number of worker threads that are going to be generating load. However, this load generator is going to be configured with a rate limit. Okay, so we're going to send 5 requests per second. So I have a bunch of workers, but I use in this case I'm using a token bucket to make sure that in aggregate they're only sending 5 requests per second here. Okay, so this is a rate limited client. All right, so remember this is what we normally do to clients. And then we need to actually send that load somewhere, so we're going to send it to our origin server. I'm not going to, a lot of the rest of these, you're not going to have to watch me type command lines for lots of the talk, because we're going to just modify them as we go. And then we're going to start the load generator. All right, so we're going to spin up here, and now let's come and look at a Grafana dashboard here. And so this is really, at this point, this is not super interesting because we're not actually going to see any problems. We only have 1 client, 1 origin, but I want to just sort of orient everybody into the dashboards we're going to be looking at. All right, so down here, what we're doing is we have the origin throughput. So the origin is just counting how many successful requests and responses it's been able to generate, and we're just scraping that over time. It's also measuring how long it takes to actually generate those responses, right? And so if you remember, we configured this to have a 1 second work time for the responses. It's actually randomized. It's sort of like 1 second plus or minus some random amount, but it averages out to 1,000 milliseconds or 1 second. Up here on the client side, I've got 2 ways of looking at the throughput. So we've got a green bar, which are the rates at the HTTP 200s. So this is the success rate we're seeing. And sure enough, that's right at 5 requests per second. The blue line at the bottom, that's labeled good put trailing 15 seconds. That's the same thing, but it's averaged over the last 15 seconds. So it sort of gives a longer average, so you can see sort of the trend without sort of the jagged ups and downs here. All right, so this all looks pretty good. Okay, so now let's have a problem. So suppose let's stop the load here for a second. Let's come back over to our origin service. So it turns out origin services, they have problems sometimes. And so let's take a look at what happens if, I don't know, my latency gets doubled. Okay, so now I've got, this is the same thing, it's just going to take longer. There's lots of reasons this could happen, right? I could have accidentally introduced a performance bug into the system. I could have, it may actually legitimately be doing more work because there's more things to do, or it may have a synchronous dependency on some other downstream service that's making itself slow. All right, so let's spin that up. Sorry, there's one more thing that I have to do here, which is important. I'm actually going to make this origin server not very self-protective. Okay, so now what's going to happen, we've got our worker thread pool. I've set shed load to false. So what that means is if a request comes in and there's not a worker thread available, I'm just going to put it on a queue. Okay, and then when a worker thread becomes available, then I'm going to pull it off the queue and process it. All right, so we're going to spin that up. And we're also going to spit up the same load, right? Still 5 requests per second. And let's come back over to our dashboard and let's see what happens. See if you can think about what might happen here. So we got some graphs here. I see an origin latency graph over here on the bottom right that doesn't look super promising here. We've got the latency seems to be climbing over time. And now, instead of sort of getting successful responses, all my requests are timing out, right? Now, the interesting thing is the origin still thinks it's processing things successfully, which in fact it is. It's just that there's this big queue building up in front of it, okay? So we've actually gotten to the point where the origin latency has gotten so high, we're getting 0 successful requests. So I'm gonna stop the load here for a second, and so we can see the client A traffic fell off there. And if we wait a little bit, eventually what's gonna happen is, which we're seeing now, is the origin actually runs out of queued stuff to work on, and it finishes, and we're not measuring latency anymore. So what just happened? Okay, so anybody who's been to a popular amusement park knows what happens if you have more people showing up on the ride than the ride can actually have in terms of throughput, right? And what happens, right? A queue forms. Especially if you're in Britain, where we actually call things queues for this. In America, there's a line. But anyway, so now let's take a look at this from a queuing theory point of view. All right, so I promised queuing theory, so here we go. All right, so now we've got our ride. We've got a line forming in front of the line, or in front of the ride. And what Little's law says is this whole thing is a request processing system, right? And so Little's law applies to the system as a whole. But, and this is the really powerful thing about Little's law, it also applies to each of the subsystems. So that means Little's law applies to the queue, and Little's law also applies to the ride. Okay, and so this is how you can start to apply these things to understand what's going on. All right, I'm going to simplify my photos away, and I'm going to put this back in terms of the origin service here. All right, so now the origin server had 7 worker threads, right? That was what we set it up, okay? So that means that when we look at where requests in the system, there can only be 7 currently being worked on by the worker pool. We set the average response time to 2 seconds. That was what we configured it to do. And so, so now we get to do simple arithmetic. And so that means that this is processing things at 3.5 requests per second. Okay, everybody with me? 7 divided by 2, 3.5, okay? So the worker thread pool is able to pull through 3.5 requests per second. And so that means that actually that's the rate at which things can drain out of the queue as well, right? So that means the queue also has a maximum throughput of 3.5 requests per second, because that's actually how requests get out, is by being pulled by the worker pool threads. But here's the problem. Our client is injecting 5 requests per second. Okay, so requests are entering the queue faster than they're being drained. So how many things are going to be in the queue? Well, if you wait long enough, there's going to be an infinite number of things in the queue. And so, so if I divide infinity by 3.5, I think that's infinity. So we start to get an infinite response time. But now actually we can take it up to the whole system, right? So now the whole system as a whole is what the client actually sees. So the interesting thing, right, is we actually saw the origin server, we actually saw this, right? We actually saw the response time growing without bound on the latency. And yet the origin server was still processing things for the worker threads, right? It still had throughput that it was still getting through. So number of requests present in the entire system, well, that's the number of requests in the queue plus the number that are in the worker threads, right? So that's infinity plus 7, which is infinity. The response time is the amount of time you spend in the queue plus the amount of time you spend being worked on. That's infinity plus 2, which is also infinity. And I'm not exactly sure what x should be here, but it's not something that we really understand. So this is the thing, right? So when we think about an API management gateway, right, we could put one of those in, and we could say, hey, I want you to limit that client to 5 requests per second, right? So because the request from the client is going to pass through my proxy, which is going to decide whether to accept it or not, pass it on to the origin, and then the response is going to come back through the proxy, right? This is how most API management gateways work. So the client's sending 5 requests per second, right? And that's actually its quota, that's its rate limit. And so the proxy's like, yeah, go for it. That sounds good. But the origin was having problems, okay? So the origin is not happy. And in fact, because the origin was not able to protect itself, and I'm not going to ask people to raise hands about how many people actually actively shed loads out of their services, but it's actually really hard to know what the capacity of your service is to be able to protect this. So it's actually common that you run into services that won't protect themselves this way. So we're stacking up all these questions, but that means that the number of open connections at the proxy that's waiting for all this stuff to happen on this unhappy origin is also stacking up. And if you're not really careful, that means that your API management proxy can be unhappy. And you can get starved out of resources at the proxy, which could have implications for other services that are being protected by that gateway. I have actually seen this happen in production. It's not super fun. So let's not do this. So what's the problem here? The problem is that the rate limit doesn't actually push back on the client when the origin is having a problem. Okay, and so let's look at it as an alternative. So we're going to apply Little's law now to the combination of the proxy and the origin. And so we want the client to be able to send 5 requests per second, right? That was its quota. And under normal operating conditions, we know the average latency of the service is 1 second, right? That's how we want things to work. So with Little's law, we said that, okay, well that means on average, there should only be 5 requests in flight at any given point in time. So here's the first idea. The first idea is that actually instead of setting a quota on a rate limit, let's actually limit the number of concurrent requests, right? We'll apply Little's law and we'll say, we're going to keep you under 5 requests in flight, okay? And it turns out this is actually really easy bookkeeping, right? So a request comes in from the client, +1, pass it on to the origin. Response comes back from the origin, -1, right? So the bookkeeping is really easy for this. And so if a request comes in, which would be sort of the 6th request in flight, right? 1 comes in, but I've already got 5, well, then the proxy just says nope, right? You know, that's where I'm going to push back and say, no, you can't send that request. So now let's look what happens if we're going to use that as a quota of the 5 concurrent requests and the client actually tries to exceed the sort of rate limit that it wants, right? So this is where we usually think in terms of applying rate limits to clients. So I'm going to try to send 9 requests per second. So what Little's law tells us, if we go and do the math, is that by counting how many requests are in flight, actually what the proxy is going to do is actually just going to pass 5 requests per second on to the origin, and it'll send nopes at sort of 4 requests per second, right? So the important thing to understand here is under normal operating conditions for the service, limiting concurrent requests behaves the same way from a client's perspective as rate limiting does, okay? So at least we've cleared that bar, right? Like we're doing at least that good. But there's something better, okay? So now let's look at what happens when the origin latency spikes, okay? And it may spike because for a variety of reasons, it may be overloaded, for example. So we need to make sure that we're going to end up limiting the total number of concurrent requests to under 5. And so in order to make this true, that means that we're going to end up limiting the throughput we're going to allow to the origin to just 2.5 requests per second, okay? Because in order to make that inequality work, right? To keep them under the quota. And so what that means is the client is actually going to receive back pressure, right? They were sending 5 requests per second. The origin's having a problem. Now I'm only going to let them send 2.5 requests per second through. Okay, this is actually what we want. If you remember, the latency on that origin service didn't actually drain off until we actually stopped sending so much load. Okay, so this is a problem, right? An overloaded service, is not going to get better unless you actually back off of it in some cases. All right, so the first thing that we want to take away is that when we look at managing capacity through API, we can actually limit concurrency and not request rate because it actually behaves a little better when we get into these overload conditions. All right, but now let's change the scenario a little bit. Suppose our origin service, instead of just having 7 worker threads, let's say it had 20. And so we elevated the latency from 1 second to 2 seconds, right? So now what's going to happen, so we're going to send the same load over to it, and we'll pop back over to our handy dandy dashboard. And what we're going to see here in a couple of seconds is even though the origin latency is in fact elevated, right? We're up around 2 seconds, which is what we expect. The origin is still able to process. Actually, now it's processing 5 requests per second. Okay, and in fact, if we look up here, the client is having success here. So wait a minute. So what just happened? Okay, so we looked at a situation where okay, we're going to limit concurrency. My origin service had elevated latency, but in one case that caused sort of infinite queuing, and in the other case it was fine. Okay, and really what we're getting at here is that throughput is not the same as capacity. Okay, and it's often the case that we use these terms interchangeably in our industry, but they're not the same. Little's law, actually, these are two different variables in Little's law, right? And so these are different. And so what I did, right, when I changed the number of worker threads from 7 to 14, I added capacity, right? I added more flying elephants to my ride, more places for those requests to sit. And so I no longer, at this request rate, actually exceeded the capacity of the ride, okay? So that's an important thing to look at. But how do we tell? Right? Like there was no way, I mean, we could see that because we knew what the capacity was. But what about our API management proxy, right? We don't want to, just because the elevated latency, in some cases, we don't necessarily want to push back because maybe the origin actually had capacity available for the same request rate even at a higher latency. Because we don't want to end up with sort of wasted pie, right? It's like, okay, here's your slice, here's your quota, and you know, yeah, I've got all this extra pie, but you can't have any. This seems sort of, you know, not intuitive. So what we really need is a way to understand what is actually the capacity of that origin service. And so, you know, a good question is, well, let's see. Can we think of any other cases where we're trying to figure out capacity or throughput and we don't necessarily have direct access to it, but maybe we can sort of run some experiments and try to figure out what it is? Well, it turns out there is. This is the way TCP congestion avoidance works, right? So TCP congestion avoidance works under a principle of additive increase and multiplicative decrease, right? So the idea with TCP is that I'm going to slowly increase the rate at which I'm sending data until I encounter dropped packets, and then I'll interpret that as congestion, and then I'm going to back off, okay? And that's the way flow control for TCP works. So let's try to apply the same thing to our proxy setting, okay? So when things are going well, and we have clients who are requesting sort of additional capacity, well, maybe we can allow additional connections back to the origin service, right? If things are going well, let's go ahead and try to service all those requests. But we're going to limit this so we can increase this by a constant factor per unit time. So in the demo I'm going to show you, it's going to be 1 connection per second. We'll sort of allow 1 additional connection to the origin every second, you know, if there's actually a demand for additional connections. And if things are not going well, then we're going to back off multiplicatively, which is a hard word to say. But anyway, what we're going to do is we're going to say, hey, our estimate of the capacity of the backend service, we're actually going to set it, in our case, to a fraction of its current size. And so for the demo, we're going to set it to 75% of what we had, right? So we're going to increase by 1 per second. And when we encounter sort of some problems, we're going to back off to 75%, okay? And we're going to try to adaptively find the capacity. So what is this, you know, sort of indications that things are not going well? Well, these could be explicit, right? So the origin service could actually pass us error codes, or maybe set a warning header, or some other indication that, hey, you're like kind of overloading me now. And so, but they may also be implicit, right? So one of the other things that you may see is that, you know, my requests to the service are timing out, right? Or I can't connect to it, or even just establishing connections are timing out, right? Those are all indicators that I might be overloading a service. All right, so let's take a look at this now. Okay, so let's set up our origin service. Okay, so I'm going to set it back down to the sort of capacity constrained version that had 7 worker threads and a 2-second average response time, and it's not protecting itself, right? So this is the same thing that we just saw, where the latency went, you know, through the roof over time. All right, now I'm going to spin up a proxy over here. So what this is an Nginx instance that has the algorithm that I've just been talking about implemented as a Lua extension. Okay, so we're going to spin that guy up. And then we're going to send the same load that we were, right? Now remember, when we sent it directly against the origin service, this knocked over the origin service. Okay, and so all I'm going to do is I'm just going to update the target so that the traffic actually goes through the proxy instead. Okay, so let's see what's happening over here. We now have an additional thing to look at. So So we're also scraping some metrics from the proxy. So there are 2 lines here. The orange line at the top is the proxy's current estimate of the capacity of the backend service. So that's the target number of connections. And then the green line are the total connections that are actually being used, right? And so as additional load comes through, what we're seeing is that we get this familiar sort of sawtooth pattern, right? So we have a demand for additional connections. We keep exploring. We encounter some back pressure, and then we exponentially back off, okay? So we're adaptively finding the capacity of the origin. Now down here, we're doing a good job of protecting things, right? Like the origin latency is not running away from us. It is going up and down. That's because the back pressure signal that we're actually using here is an implicit one, right? We're getting to the point where we're actually timing out. We can see some of those timeouts up here. This is the blue line up here on the client. So we're seeing some timeouts where the queue is getting too long and the proxy backs off, okay, based on that signal. And so based on that, the actual throughput we're allowed to get through is going to vary with the current number of connections, right? This is Little's law again, right? There's a relationship between those things. So this is working, okay? This is working pretty well. So let me stop this load and let's go back to the queuing theory. All right, so what's going on here? So in this situation, we still had 7 worker threads at the origin. We had 2 seconds of average response time. And so that we still have the same 3.5 requests per second throughput that we're able to get here. Now, if we want to actually sort of stay within that maximum throughput, that means that the throughput that we actually want to see for the whole system and the throughput of the queue also have to be 3.5 requests per second or less, right? That's the whole point. That's what we're trying to do. We're trying to stay within what that origin service is able to do. So now, in our case, we had a socket timeout of 2.5 seconds on the client side, okay? So in order to get good responses from the origin service, I need the response time as a whole to be less than 2.5 seconds, okay? But that means if I'm spending 2 seconds in the worker thread, I can only spend half a second sitting in the queue, which means on average, I have a queue length of 1.75 requests sitting in the queue at any given point in time, on average. And so that means that, that the total sort of concurrent connections that we want to see here has to be 8.75 or less. And this, we actually left it, I stopped the proxy and this left off, but it may be a little too small to see, but in triumphant proxy or demo success, the target connections actually stopped at 9 concurrent requests. So we actually, with this algorithm, we actually found what the queuing theory predicted was going to be the capacity that we needed to limit this to. All right, but that's not all. There's more. So I've shown you how to adaptively determine the origin capacity. But of course, so far we've only been looking at one client. Okay. Now this has been my experience of how capacity gets managed when you have sort of in an enterprise where you have lots of services, right? I've got client A that says, hey, I'd like to use 50 concurrent requests. Actually, a lot of times they're not used to asking for concurrent requests, so we have to sort of teach them about Little's law. But say, hey, I want to use 50 requests. And so then we go and we actually talk to the people that run the origin service, and they say, okay, well, I actually have capacity for 200 concurrent requests. 50 is less than 200, so okay, you're good to go. And we set a quota for client A of 50 requests, right? Then client B comes, and they say, I'd also like to use 50 concurrent requests. And the origin says, okay, I've got capacity of 200, and I gave 50 to those folks, so yeah, I can give 50 to you too, and so that's okay. And so I set a quota for B of 50 concurrent requests. And then we actually see what happens in production, okay? And one of the things that I commonly see is that client A uses 10 and client B uses 10. Because they've asked for conservative quotas. That's actually a sort of a standard. It's just like when you build a bridge, like you build it to support like way more trucks than will actually cross the bridge, right? And so what we end up with is we end up with stranded capacity, right? So so what ends up happening is that we've got client A and client B are using this slice of pie, but we've got all this wasted pie, and you may get a theme. I don't like wasting pie, so. So now there's another scenario that happens, which is that client A may actually come along and attempt to use 60 concurrent requests, right? And this sometimes happens where a client A may be running a service that's actually gotten more popular, it's starting to take more traffic, but actually forgot to come and update their quota, okay? So, so if we actually just enforce the quota of 50 concurrent requests, right, we're actually going to say, the proxy is going to say, well, wait a minute, 60 is bigger than 50, so I'm going to start, sending nopes for the extra 10 that you're trying to send me. But here's the problem, right, which is that the origin service, right, we're only trying to use 70, and I certainly have the capacity for this. Okay, so this is the case where sometimes the quotas are actually being too aggressive, right? These are requests we could have served, but we're actually enforcing the quotas strictly, and so we're actually not serving requests that we could have served, right? So these are, in some sense, avoidable errors. All right, so now let's try to figure out what we're going to do here. So we have an idea because we can, part of the problem here was we didn't realize that the origin service had additional capacity. Okay, but we actually just saw a way that we can adaptively figure out what that capacity is. So now the idea is, okay, well, rather than having a flat sort of absolute number for a quota, what I'm actually going to do is I'm going to give you your configured quota percentage, and I'll explain what this is, times my current target connections, right? I'm going to have my target connections with my estimate of the number of concurrent requests I can have, and so then I'm going to hand those out on the basis of sort of what your configured percentage is. And so that means that now we have, when a request comes in from a client, and we have to decide whether to admit that request, we're going to do one of two things, right? So first we're going to say, hey, is the number of concurrent requests you're trying to use currently less than sort of your fair allocated configured percentage of the total capacity that I think the origin service has? And if it is, yeah, hey, you're sort of within your quota from some point of view. And so I'm going to let that in. Or I may also let it in if the total number of connections that are coming through is less than the target, right? So I've actually estimated that even though you're going over your quota, the origin has room to handle your request, right? That was the scenario that we saw there where client A just went over. And so we're going to try to make that work. Okay. And so now I'm about to show you another scenario. So in this scenario, what we've done is we've configured quota A to say, so we've actually written down, hey, we want to give 5 concurrent requests to client A. We can give 15 concurrent requests to client B. And so that means that essentially client A is entitled to 25% of the available capacity. Client B is entitled to 3/4 of the current capacity. All right. So now I have a video because the laws of demos plus the fallacies of distributed computing say you should not run a network demo during your talk. So I actually took a video of this because I couldn't actually run it from a machine because there's a limit to how many sort of connections you can hairpin through the loopback interface over a bridge Docker network interface. So, all right. So here's what we're going to do. Okay. So I'm going to start up the same proxy that we just saw, right? This is the one now. This has been configured with the A is entitled to 25% and B is entitled to 75%. We're going to come over here on our origin server. We're going to spin that up again. And we're going to give it a little more capacity just so that we can sort of see this a little more effectively. So we're going to give it 40 worker threads, and to make the math easy, because it's easy for computers to divide by 2, but maybe not so much for folks in an audience or a speaker for that matter to do it on the fly. So we're going to have an average latency of 1 second. So we're going to spin up our origin, right? So that origin should have a capacity of 40 concurrent requests. All right, so now let's come over. We're going to spin up some load from client A. Now remember, client A is entitled just to 25% of the available capacity. So it should only be entitled to like 10 concurrent requests. But we're actually going to send 40 requests per second, right? Client A is going to be sort of really aggressive, and it's actually going to try to use the full maximum capacity of the origin service. And we're going to send that load through the target here, right, at that proxy. So we're going to spin that up. Now we're going to come over to client B. Okay, so client B is actually not going to be aggressive. It's actually going to stay within its configured quota. Actually, it's going to even stay within its actual quota. So we're only going to send 12 requests per second. It was actually configured to be 15 absolutely, but it's entitled to 75%, right? So it should be entitled to 30 concurrent requests, and so we should be, well within what client B is allowed to use here. Okay, so let's see what happens. So we come down here, we're going to look at our proxy. So this is actually climbing its way while we were launching stuff. It's been climbing its way towards 40 concurrent requests, right? It only adds 1 per second, so we actually have to wait for the traffic to sort of catch up with us. If we come up here and look at client B, we can actually see client B is actually already getting its 12 requests per second, which it was trying to do. So we're actually admitting the traffic that we wanted to admit from client B, which was staying within its quota. The orange line there that's sloping up, again, that's that trailing 15-second average, and so we have to average out the zeros that we were seeing there. Over here on client A, we have the same trailing orange line, and that's showing up a little, looks to me like 23 concurrent connections or so, 22. And so what we're seeing, so it's trying to use 40, it's allowed to use 10, but there's all this unused capacity, and we're actually letting it use 22, and we're pushing back on the rest of it. Right? If we look down here on the origin throughput, our throughput is sort of varying. Again, we have a back off factor of 25%, right? So we're setting it down to 75%. So we actually sort of drop from, when we back off, we drop from 40 requests per second down to 30 requests per second when we do that, and then we grow back up. So we sort of see it up and down, but the throughput is stabilized, the origin latency is stabilized. So we've stayed within the boundaries of the origin capacity, and we've sort of, this looks great, right? Like we've got client B is within its configured quota. They're getting everything that they're asking for, and we're sort of doing best effort. We're doing as much of client A as we can possibly serve based on the origin capacity. All right. So now, so one last thing though is that. Let's go here. So we can actually borrow quota when it's available, right? So that's really the takeaway here. So now here's the thing, right? Okay, so the reality is I don't actually just have one API management gateway, right? Usually what happens is I set this up, so I have multiple instances of these, possibly behind a load balancer, right? So traffic is going to come in, it's going to get distributed between these proxies, and so the question is, okay, how am I going to do this across multiple instances? Right? So I've got quota A at 5 requests per second. Well, I've got 2 instances. Does that mean I need to, 5 concurrent requests? Does that mean I need to configure, divide by 2 and sort of configure each proxy to just have 2.5 concurrent requests? I'm not sure how I count half a concurrent request anyway. Or do I have to have some centralized bookkeeping, right? Where maybe there's some kind of shared cache across these things, where these things are updating counts of who's using what. That could be a scalability concern. Certainly it's a single point of failure, so that's not great. And so here is the great thing about the additive increase, multiplicative decrease thing that we just saw, right? So the thing about this property is that it actually converges to a fair allocation of available capacity. Okay, so let's look at one more demo. All right, so this is the same scenario we just left off, except that the traffic is actually going through a load balancer now to our single proxy. So that's the only difference here, right? We've got our adaptive number of connections. And what I'm going to do is I'm going to come over here. I'm going to spin up a second proxy instance. This is configured exactly the same. They're both configured to say client A gets 5, client B gets 15. I'm not dividing anything. I'm just giving it the same configuration. And so let's go and see what happens. So now there's another second set of lines that's starting to show up on the proxy line here, right? That's the second proxy. Is beginning to probe its way and find additional capacity at the origin. And again, due to the additive increase, multiplicative decrease, what's happening here is that the first proxy actually backs off faster than the second proxy is sort of trying to gain additional capacity. And so what happens over time is that these 2 rows are going to start sort of finding an equilibrium and going back and forth. And so essentially the 2 proxies have evenly divided the amount of available capacity for the origin. And it's okay, we don't have to divide the actual quotas because we're actually only working on quota percentages anyway, right? So it turns out when we look back up here at the client B, it's the same thing. It's still able to get its 12 requests per second. Client A, at this point, it looks like that stopped at 23, so that's 35 out of the 40, which again, because sometimes we're backing off to only 30 requests per second when we back off, that's actually pretty good, right? So we're actually able to do this dynamic and adaptive sort of thing without central coordination at the proxies, which makes this pretty cool, I think. Whoops, we don't need to see that demo again. Well, I mean, unless you want to, but. All right, so that's what I have to say here. So there's a few things that I want you to take away here. So the first one is Little's Law is great. If there's one thing you should take away, it's like you should write down Little's Law, okay? And now all my coworkers are laughing at me. But seriously, it's a great way to understand sort of the capacity of your request processing system, right? You can break it down into different subsystems, think about where requests are sitting, think about, okay, how many of the connections in that connection pool are being used, how many file descriptors are being used, right? And you can figure out where you're starting to run out of capacity. In terms of API capacity management, I think it's actually a lot better to limit concurrency rather than request rate. And that's because when you have an overload condition at the origin, limiting concurrency actually provides the back pressure on the clients that you need in order for the origin to be able to recover in those cases. I've also shown how to adapt to the capacity of the origin, right? The origin service might be in an elastic scaling group, right? So it could be that actually it will just add capacity as you send more traffic through it, right? And in those cases, we want to take advantage and not strand that capacity if it's available. And then, the last thing is we've shown a way where we can actually borrow unused quota from other clients to make fuller use of that capacity. And so, what this all boils down to is that we can still protect the origin services, which was the idea of rate limiting. We can keep the allocation of capacity between clients fair, but we can sort of make still a best effort approach to serving as many requests as we can. And so I am slightly over. I guess I need to drink one more cup of caffeine, but I'm happy to take questions after this. You can either find me here or I'll be at the Comcast table between breaks today. So thanks.